Resonance. We saw that with a pure inductor, as we increase our frequency, we find that due to the frequency, we get due to the formula, we get a linear increase in the inductive reactance, and for the capacitor we find that we get a non-linear decrease. Now what we find is at this specific point where these two meet, that is my resonant frequency. Now at resonant frequency, the inductive and capacitive reactances are equal. As a result, what that basically means is the circuit is in harmony, that the amount of energy stored by the inductor and the capacitor is the same. In a series circuit, the voltages over these two components will be equal. In a parallel circuit, the current flow through each of these components will be equal. We find in the resonant circuit, when it comes to series, that the impedance is at its lowest point, and as a result we will have a maximum current flow. Conversely, in parallel, we will have a minimum amount of current due to the maximum amount of impedance that is generated. At resonance, because the inductive and capacitive reactances are equal, we will have a phase shift of 0 degrees. So we can either say that the circuit is at resonance or the circuit is at unity. Now, in order to calculate the resonant frequency, we know that XC and XL are equal. So we can say that you're welcome to do this on your own. XL is equal to XC, and if we substitute these two formulas into this, and we move all the frequencies to the left and we move everything else to the right, we find that the resonant frequency is the inverse of 2 pi times the square root of LC. That is the formula to calculate the resonant frequency. When it comes to the graphs at series, we find that as we increase our frequency, we will have, take note this is not to scale, we will have a graph like that represents the current flow, and we will have a graph like that represents the impedance in the circuit. So at series, inductive and capacitive reactance are equal. As a result, the resistance is equal to the impedance. Impedance is at minimum, current is at maximum. Because inductive and capacitive reactances are equal, the inductive voltage is equal to the capacitive voltage. Total voltage is equal to the voltage on the resistor. Phase angle is equal to 0 degrees, and the power factor is equal to 1. For parallel, we will have the same typical graph, but we find conversely that the impedance increases around resonance, and as a result the current decreases around resonance. Total current decreases around resonance. Again, inductive reactance and the capacitive reactance are equal. As a result, the resistance is equal to the impedance. We find that the impedance is at maximum and the current flow is at minimum. Because this is a parallel circuit, we know that the capacitive current and the inductive current are going to be equal. The resistive current is equal to the total current. Again, phase angle is 0 degrees and the power factor is equal to 1. Now at resonance we get the ability of generating a specific bandwidth, and this is done by means of the Q factor. Q factor is the ratio of energy stored to the amount of energy converted. Q factor only applies at resonance. Now the formulas that we use: Q equals 1 over R times the square root of L divided by C, or we can use Q equals XL over R. And conversely, because the circuit is at resonance, XL and XC are equal, so we can also say XC over R will be equal to my Q. This applies both in series and in parallel. The bandwidth shows the efficacy of the circuit over a range of frequencies. When we look at the gain graph, we find the circuit, the waveform looks like that, representing the frequencies, and we find that the resonant frequency is indicated right there in the middle of the peak. Now to calculate the bandwidth, in other words, the halfway mark, that's done at 0,707, if that is 1. That is 1, that is 0,707 or 70.7% of the maximum, and that level will indicate my bandwidth. We find there is our lower frequency and there is our higher frequency. And in order to calculate that bandwidth, we use the formula bandwidth is equal to the resonant frequency divided by the Q factor of the circuit. For more specific values, we can say the bandwidth in series is equal to I max divided by the square root of 2. And if you calculate that, that's equal to 0,707 if I'm not mistaken. For parallel, we use the same formula except we replace it with maximum impedance divided by the square root of 2, and that is bandwidth.